I did.
Have you done this one?
Yeah, but I got wrong.
Not wrong. Okay, that's your wavelength. That's your second wavelength. That's half a wavelength. Right? So it's 2.5 wavelength is 39 cm. So your wavelength is 15.5 cm. If the frequency of oscillator is 2000 Hz, what is the speed of sound? V equals to FF. Change it to meter. Right? Frequency is 2000 Hz. Multiply out is 312 meter per second. Okay, anything not clear?
Yeah, can.
If you're asked to put a node, antinode, then there's where the antinode is. Try this one, microwave. Even though I didn't teach you, three, there's an example. Microwave transmitter emits wave that reflect from a metal plate. There's a metal plate. There's a source of sound. A detector. There's a detector. Picks up the standing wave. Produce R, S, and T are three adjacent points at which the meter shows zero intensity or zero current. Zero intensity, zero current. What's the frequency of the emitted waves? What's your answer? Ken,
Yeah.
they told you R and S and T are the nodes, so draw the picture that way.
Oh, draw the. Oh, okay.
There's a standing wave, so one wavelength, no? Yeah, the paper is yours. Draw on the in the exam, draw on the paper itself. It doesn't matter. Only at the nodes are the intensity zero. At the node, the displacement is permanently zero. Right? So RT is one wavelength, 3 cm, and the frequency. Right? If you use microwave, is the speed of light equals to f lambda. So frequency is just 10 to the power 10 hertz. So
Okay, yeah, got it.
can donkey.
Can.
Okay, I think we will go to a new topic. Okay, page 194. Right? That's the phenomenon or what you get for diffraction or paperclip. Right? That's the syllabus. Okay, yeah, you do not interested in great detail, not the maths part, just wide gap, narrow gap, and wide gap. So that is your triple tank experiment. That's the water waves. Right? That's the obstacle. So if you like travel in a straight line, then there's the region of shadow. So first thing to remember is what's diffraction. Memorize it. It's the spreading of wavefront into the geometrical shadow as it passes through a slit. Right? That's the geometrical shadow. Right? You can call it a gap or slit. Right? A gap or slit is two optical, one optical here, one optical there. right? A is the size of the aperture, right? So that's what you will draw lor. Or diffraction. It can be sound wave, it can be light wave, any type of wave can be deflected by an obstacle, right? Ripple tank experiment. There's your straight edge to produce plane wave. There's your gap, right? There's your barrier. Ripple tank using straight edge to produce plane waves. And wide gap between the obstacle. You can adjust that gap to be wide or narrow. Right? There's your source for your power supply. Okay, diffraction, wide gap. Wide gap means your aperture size is very much greater than the wavelength. No? So that's the region of shadow. If you think there's a light traveling in a straight line, no? So that is what you observe. Right? It's still plane wave, except that it's spreading out, right? More and more as you go further and further away. The key to remember is emerging from the gap, right? It's plane wave, slight bending of wave at the edges there, slight bending. Wavelength and frequency of the emerging wave say the same as the original wave. Wavelength doesn't change. That's your wavelength. Between wavefront is your wavelength. It hasn't changed, right? Frequency hasn't changed. Narrow gap, narrow gap where your aperture size is almost equal to the wavelength. Right? You can think of your narrow gap as a point source, so if you like. So plane wave becomes circular wave. Gap is about the size of wavelength. The emerging wave have circular waves. The wave have spread into the region of shadow. Right? That's the region of shadow. That's the region of shadow. Okay, behind the obstacle. So that is your large gap. That's your narrow, small gap. If it's exactly the same, then it will be completely spherical. Wavelength of incident and diffracted wave are the same. Right? Have wavelength doesn't change on diffraction. Amount of diffraction depends on aperture. Right? There is slight diffraction. There's a lot of diffraction, small gap. Okay, diffraction across an obstacle. Example, a hill. Right? This one has to do with radio wave. Right? That's your plane wave. That's the obstacle. So long wave tend to curve more, yeah, or diffract spread out more lah, rather than curve more lah. Diffracted more or spread out more. If the wavelength or wave is shorter, the spreading or effect or diffraction is much smaller as well. Right? Smaller diffraction, short wavelength. Right? It has to do with television wave, no? Diffraction or radio wave over a hill. Right? There's a hill, there's a shadow of the hill. So television wave, the shorter wavelength, so it is spread out less, diffraction is less, so it would be a problem lah. The person here receiving the television wave, but he can receive radio wave, longer wavelength, right? Because longer wavelength bend more or diffracted more. Long wavelength are better at bending around obstacles such as building than short wavelength. That is why it is difficult to receive good television picture when your house is in the shadow of a large building or hill. The diagram shows the bending of long and short wave. That's called diffraction. There's short wavelength. There's longer wavelength. Right? For light, you can use a pen light laser. And then there's your slit there, single slit. There's your pen laser. That's what you observe. Right? Bright, dark, bright, dark. The center one is wider lah. Don't need to go too detail lah. Just roughly lah. Not mention your syllabus. Diffraction is on the horizontal side, right? This side. Diffraction is on this side. That's why you see the images there. You don't see on top there. There is no diffraction here. This is white gap. Incident light can be from a laser pen. Right? If it's a spherical, diffraction is all around the circle. So we see spherical wave. Sorry, we see spherical images. Right? There is 80% of the intensity. This one is less than 80%. Smaller aperture, the larger the center spot, the brighter, and the larger will be the center spot if this aperture is small. Right? We see concentric, bright and dark ring. This is more to prepare you for what you study in A2 lah. AS not required at all lah. But this is the effect of diffraction. No? At the center of the screen, there is a circular spot of light that contains 84% of the light that passes through the aperture. The smaller the aperture, the larger the spot. No? Circular bright spot. Right? This diffraction around the aperture, not one side only. Right? For light, that's the intensity. That's the intensity over, again, distance curve. We won't go into detail. I think we will stop here. Okay, let me let you watch a video first. Can hear? Raylan, can hear?
Can you, I am not sure. Cannot,
Can?
cannot.
Cannot lah.
Yeah, cannot.
Hey, what's wrong with that?
Meet. They interact with each other.
How about now?
Yeah, can.
Can, okay.
Interference of waves. When two or more waves meet, they interact with each other. Interference is a phenomenon in which waves, from two coherent sources passing the same point, reinforce or cancel each other. Coherent sources of waves produce waves of the same frequency and a constant phase difference. When water in a ripple tank is disturbed by two coherent sources, the uniform pattern of ripples can be observed as shown in the diagram. The source of waves is coherent, which maintain at a constant phase difference and same frequency. Such a pattern of ripples is produced when water waves which are approaching each other meet and overlap. The waves are said to be undergoing superposition, and the phenomenon produced is known as interference. The principle of superposition states that the resultant displacement at any point where two similar waves cross is equal to the sum of the separate displacements of the two waves. Wave interference occur when two waves that are traveling in opposite directions meet. The two waves pass through each other, and this affects their amplitude. There are two types of interference: constructive interference and destructive interference. Constructive interference occurs when the crests, or highest points, of one wave overlap the crests of the other wave as shown in the diagram. As the waves pass through each other, the crests combine to produce a wave with greater amplitude. Destructive interference occurs when the crests of one wave overlap the troughs, or lowest points, of another wave as shown in the diagram. As the waves pass through each other, the crests and troughs cancel each other out to produce a wave with zero amplitude. the ripple tank experiment for studying interference of waves, the spherical dippers can be used to produce coherent sources. Antennal lines consisting of maximum crest and maximum troughs, when constructive interference occurs. It's a line consisting entirely antinodes. Nodal lines consisting of points with zero displacement, when destructive interference occurs. It's a line consisting entirely of nodes. From the interference pattern, the superposition of the two sets of waves can be studied by the following formula. The distance of separation x between two successive antennal lines of nodal line depends on the wavelength. The distance of separation between the two coherent sources A. The perpendicular distance from the coherent source to the position where x is measured d. Thank you for taking time to watch this.
Okay, let's go back to our lesson. Eight by 3, interference, two source interference. Right, there's a syllabus. Interference, wave can spread out as diffraction at a narrow aperture. What happens when two or more waves meet at a point? Right? You can see in the pond there sometimes where you drop a stone in two different places there. Right? Page 195. What is interference? When two or more waves meet at a point, there's a change in overall intensity or displacement. Right? That's what you observe. That's what I call the phenomenon. Right? That's constructive interference. Superposition tells us how to add the waves. Why do we get the interference pattern? We add the waves, the displacement of the wave. Interference tells us what we see when the wave cross. Coherent is a constant phase difference between the waves. Right? This coherent wave at any distance, constant phase relationship, either constant phase relationship or if it's cross, always a cross. Right? Or constant phase, or sometimes we call it constant phase relationship. Coherent waves are locked together both in space and time. Right? Space and time. Incoherent waves have no relationship to each other. The waves all have no relationship to each other. They don't start at the same point in time and space, nor do they have the same wavelength. Right? They can start at the same point, but different wavelength. So it's incoherent. You can look at this is where they start the same point, but after some time, they are all completely different already. This is minimum, this is maximum, this is another amplitude, this is also another amplitude. So they are all different already. That's not coherent anymore. Right? So the requirement for coherent is same wavelength or same frequency. Condition for coherent. The two waves are not, if two waves are not perfectly monochromatic, means not of identical wavelength, then they will not remain coherent. Right? Important, they must have the same wavelength or same frequency, then they will be coherent. But they can have, if the waves are moving in with respect to each other, even though they have identical wavelength, they cannot be remain coherent. Like this one, different, same wavelength, right? Same wavelength, but different direction. So if you look at this, they start from the same point, but after some time there or some distance away, they are no more the same already. The cross come later on, so no more coherent anymore. Right? So it must have the same direction and wavelength. Condition for wave to interfere. Both waves must be of the same type. That means sound wave and sound wave, light wave and light wave. Meet at a point same direction of polarization. That means same plane of vibration. That one you have done already. Principle of position, when two or more waves meet, the resultant displacement is the sum of the individual displacement. Just repeating, right? These two are not same direction of polarization anymore. Stop me if I'm going too fast.
Oh,
Okay. Usually, they will draw the crust for you. Circular wave as your source of wave S1, source of wave S2. They are in phase. They are expected to understand that at the center there is the trough or minimum point, right? At the center there. So where the crust and the crust meet is called the antinodal line. Right? Constructive interference occur lah. Right? Maximum, 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 maximum. Right? So you can draw the trough if you want to, but usually it won't draw for you. So where the trough and crust interfere, crust and trough interfere, that will be your nodal line, destructive interference. Okay, and then we have that one has to travel longer distance. S2, the wave has to travel longer distance to reach that point. S1 shorter distance. The difference in length is called the path difference. Okay, we are just going into more detail. Right? S1 source of wave, S2 source of wave, they are vibrating in phase. Right? That's the same picture, except that B, that point there, is the midpoint of S1 and S2. And then AB is a perpendicular bisector. So S1B equals S2B, or any point along AB is equal distance from S1 and S2. So nodal lines are lines where cancellation of wave occur. That means destructive interference. Example, this one. The darker one is the crust. The trough is the one less dark. So there's the destructive interference of crust and trough meet. Crust and trough meet. AB is a perpendicular bisector of the source S1 and S2. All the points from AB are equal distance, AB, right? AB equal distance from S1 and S2. So the path difference is 0. Right? So path difference 0, constructive interference. Cross, trough. Antinodal lines are lines where the reinforcement of the wave occur. Right? Constructive interference. Example AB. Right? The red dot. Constructive interference occur. Cross meet cross, trough meet trough. Right? EF is the same. EF the same. Where the red dots are. Usually only the crust is drawn for you. The trough is the midpoint between the two crusts. Right? They won't draw for you all complete picture for you. They'll draw for you the crust only. Okay, example. Path difference between S1, S1T and S2T. That's your T. S1T, S2T. Okay, what's the path difference? S2T minus S1T. That's the path difference.
oh yeah.
What's your answer? Usually we calculate path difference rather than draw picture. Because picture take time. So what's the path difference? Right? For S1T, one wavelength, two wavelength. S2T, there's one wavelength, two wavelength, three wavelength, four wavelength. So subtract, you get two wavelength. Path difference, two wavelength. So this is constructive interference, whole number. So T is constructive interference. Can?
Yeah, okay. 这边 hard to see 啊。
Can't do any better than that.
啊？
Can't do any better than that.
哦，OK。
Yeah, I agree with you. Too many dots there. Got focus on the red one. This one. Path difference between S1Q and S2Q. Q is here. There's your Q. S1 is here. S2 is here. So we are interested in S1Q, S2Q. Subtract, no? Path difference is subtract S2Q minus S1Q. What's the answer? Okay, one wavelength, two wavelength, three wavelength, 3.5. Right? S1Q is 3.5. S2Q, one wavelength, two wavelength, three wavelength, four wavelength, five wavelength.
5。
So it's 1.5 wavelength. The 1.5 wavelength we see is destructive interference of cross mid trough. Okay.
OK。
How about S2P and S1P? There's your P, eh? I have to take it through, right? You come out in an objective. S2P, S1P. Yep. What's the path difference? PD is a standing symbol for path difference.
I think it's 2. S S2P is 7.
We got 10 minutes left. 1, 2, 3, 4, 5, 6 only.
6 啊？
6, you can see. 1,
係啊。
2, and S1P is 4. 1, from here to here is 1, 2, 3,
No, that's Q.
sorry. 1, 2, 3, 4. 4 lambda. Okay.
OK。
So constructive interference. Usually for light, we put a screen there lah. So the center one is called 0 lah. Path difference 0. And then the blue dot, the first blue dot is half a wavelength on both sides. And the first red dot is wavelength, no? One wavelength, path difference. And then the second blue dot is or destructive interference or dark band is 1.5 wavelength, no? So in general, the path difference is the extra distance which a wave travel compared to the other one. So path difference, whole number, constructive interference. Right? You can use M or you can use N. No? Path difference of half a wavelength. Right? Or we can summarize it. Half a wavelength, 3/2 wavelength, 5 lambda over 2 wavelength. Right? Destructive interference. Okay, either this formula or that formula is the same. Right? So if it's like constructive interference here, path difference 0, and then the first one, count M equals 0, M equals to 1, M equals to 2. So that's a 2 wavelength path difference. Right? can use, some textbook use M, some textbook use N, doesn't matter. It's called the order of interference. M equals 0, 0 order. We call it center bright fringe. So if you use light, M1, first order, first bright band, right? We can use ripple tank experiment. Right? We can use two sphere and then connected to the same source, to source interference. Or we can use optical, right, with a gap in between. Microwave, metal reflects microwave, cardboard reflects partially. Receiver can be, this is an emitter, right? Or you can connect it to a loudspeaker, can connect to a loudspeaker. That's your detector that we see just now. This is a probe. This is also a detector, different one. Right? You are free, can go and read this one. Won't go into that. Right? Microwave, the range in wavelength is 0.01 to 10 cm. Right? That's a setup from when we use microwave for double slit interference. Okay, so we use the gap is about 3 cm. Right? You won't bother about that. Lamp is not a coherent light source. So we can use this is for illustration only. Mistake in concept, I cannot use a lamp. Right? Cannot use a lamp to produce circular wave. Need a single slit. Need to put a single slit first. And then lamp is not a coherent light source. It gives out more than one wavelength. So for microwave, there's a transmitter. Right? From center to center is 6 cm. And then the slit, our aperture size is 3 cm. There's your probe or receiver detector. Transmitter emits microwave. Two wave train emerges from the 3 cm wide slit. Right? Emerges from this slit. These are coherent source. Right? The transmitter must be at the perpendicular bisector of the two slits. The detector is moved along the line perpendicular to the central line. That's the central line. Right? Move along the line there to detect the intensity. Zero intensity and high intensity. Receiver detector detects maxima or minimal intensity and are shown as high and low on the, right? That's your meter. To read the current, I show current. Requirement of interference in two sources must be coherent, same frequency, same speed, same amplitude, same type, and plane of polarization. That's for light. Source close to each other. In young double slit experiment, we are using narrow slit. Right? Both slits are narrow slits. Screen slit distance large. Right? So single slit, double slit, and right? This is your screen. There's a double slit, there's a single slit, they are all parallel to each other. Single slit at the perpendicular bisector of double slit, right? At the midpoint of here is a single slit. Observations, you see bright and dark bands evenly spaced. Sodium lamp provide yellow light diffracted by the single slit. And then the two wavefront coming out from S1 and S2 are coherent. They're from the same wavefront from the single slit. So the S1 and S2, slit S1 and S2 called diffraction. Interference occur in this region only. Right? This is only one wave there, only one wave there. Only in this region called region of interference, you have the two wave interfere, wave from S1 and S2. Right? Can call it Y or can call it X, depending on the book you use. Right? So there's your D, distance between the two slits. There's your Y, from center to center. Single slit, double slit, screen, aperture, size, slit spacing. Right? Your textbook or some syllabus that be a bit confusing lah, because they use this one for A lah. Okay, I use D because it's consistent with diffraction grating lah. Slit screen distance, I think we still got quite a fair bit to cover lah. So if we get cut off, then we'll carry on from next week. We still got about 1 minute left.
Yeah.
Characteristic, alternative bright and dark, evenly spaced fringes are observed on the screen. Right? Evenly spaced. Number of fringes or bands obtained depends on the amount of diffraction occur at the slit. And this in turn depends on the width of the slit. Right? Depend on the width of the double slit, or the interference pattern here lah. Fringes are found only in the region of overlap. That's the region of overlap. Right? Region of overlap. It depends on that one there. It's wide, the interference region will be small. Narrow gap, interference region will be large. Right? That's the intensity distance graph lah. It's called threshold of vision. Threshold of vision basically tells us that our eye cannot see below certain intensity, our eye cannot see anymore. So we see as instead of dark line there, we'll see as dark band. Right? So below that intensity, we cannot see anymore. That's why we see as dark band,